Okay, so this is our continuity and symmetry notes. So we're going to start with a warm-up. You can go ahead and pause the video and do this warm-up. It has things to do with what we learned yesterday and the day before, I should say, the previous lesson and the lesson before that. All right, let's see how you did. The first one's find f of -1. So you can go ahead and plug -1 into the function for x. -1 squared is +1. 2 times 1 is 2 minus 1 is 1. So f of -1 is +1. Next one, if f of x is 7, what is y? So we are going to change f of x to 7, the question was if f of x is 7, what is x? So we're going to change f of x to 7. Make sure you don't plug in 7 for x. Let's change the y value to 7. And we are going to solve for x. So add 1 to both sides. 8 equals 2x squared. Divide both sides by 2. 4 equals x squared. And now we need to solve for x. Remember, to solve for x, you can square root. But remember, whenever you square to solve, you have to account for the positive and negative solutions. So this is going to have 2 solutions. X equals both positive and -2. If you check both those x values, they both give you the output of 7. Plugging in 2 squareds, 4 times 2 is 8, minus 1 is 7. -2 squared is also 4. That's why it's going to give you the same output. All right, next one, find f of -x. So we are going to plug in -x for x and see what we get. So that is 2. Plug in -x for x, square it, minus 1. All right, clean this up. So first off, I need to know what -x squared is, or -x times -x, which is x squared. And multiply it by 2, which is 2x squared, and subtract 1, which is -1. So f of -x is 2x squared minus 1. So we got the same thing we started with. That is a concept that we'll be using later, so that's why we're having you practice it now. All right, next one, does f represent a function? So is it a function? So let's go ahead and look at the equation, okay? All right, so remember, a function, for every input, there's exactly one output. So I could ask myself one of 2 questions. If I plug in an x value, will I ever get 2 outputs? So like if I plug in 1, will I get 1 answer or 2? If I plug in 1, I get 1. That's 1 answer. When I plug in 0, I get -1. That's 1 answer. Is there anything that's going to give me 2 answers? No. So every input does have exactly 1 output. Therefore, it is a function. I only tested 2 numbers, but I'm running through a bunch of them in my head. Another reason why I know it's a function is think about what this is. This is I should go like this. Think about what this is. This is a quadratic equation. A quadratic equation looks like a parabola. This is an upward-facing parabola. So if you look at it, it passes the vertical line test. So we can say, yes, this is a function. It doesn't ask us why, but let's say passes vertical line test. Vertical line test, I'm going to shorten to VLT. And I'll draw the picture right here, right next to it, so we realize why. All right, what's the domain of the function? You can look at the graph that we just sketched and say, oh, it goes from an arrow. If I look to the left, an arrow to the right, all real numbers. Or we should do what we've been learning, right? Look at the equation. Are there any restrictions? Are there any denominators? No. Are there any square roots? No. Therefore, are there any restrictions? No. So our domain is all real numbers. No. Last but not least, describe the end behavior using limit notation. So we're going to say the limit as x approaches -infinity of our function, which its name was f of x, is, so we're going to look left on our graph with our eyes, right? So as our x values get smaller, what's happening to our y values? We did this sketch right here. That's an arrow pointing up. So that is positive infinity. And the limit as x approaches infinity of f of x. So if we look with our eyes to the right, or as our x values get bigger, so are our y values. So this is also infinity. Okay, on to the new material. So what we're talking about today, as I said before, one of the things is continuous functions. So what is a continuous function? The picture to the right here, this is a continuous function, okay? If you look at this definition here, it says the graph of a continuous function has no breaks, gaps, or holes. In other words, a nice way of thinking about it is that you could trace the graph of a continuous function without lifting your pencil. Now, some people try to get, funny about this. And if I said, oh, can you draw this, okay, without lifting your pencil, right? Some people will say like, yes, I can, look, okay? That's not what we mean here. This open point right here, okay, that means that there's nothing there. So that's actually what it looks like, okay? You can't draw that without lifting your pencil, right? We put the open point there so you can actually see it with your eyes that there is a gap right there, okay? All right, so looking to the right here, this is a continuous function. You can draw this without lifting your pencil. All right, looking at these three right here, these three graphs you cannot draw without lifting your pencil. So these are all called discontinuities, and we have to know what type of discontinuities they are. So if you look at right here, this graph right here, we have this piece that you could draw without lifting your pencil. Not talking about drawing the arrows on the end, but I could still do that. But then you also have to pick up your pencil to draw this piece, okay? So the gap or the discontinuity is located in between these two pieces. So let's draw in what's actually happening at that gap, okay? We have this dashed line right here. This dashed line, as you recall, is called an asymptote. So if there is an asymptote in your graph, to show that the graph is gliding up against that, but there's nothing there, that's a discontinuity. The type of discontinuity that's called is an infinite discontinuity, okay? Now, how are you going to remember that's called an infinite discontinuity? How I've told my students in the past is that an asymptote goes on forever and ever in both directions, infinitely, infinite discontinuity. Our next type of discontinuity, once again, if I draw this piece, I have to pick up my pencil to draw this piece. So if you look at where there's a gap, the gap is right here, okay? That gap right there, notice that this piece, you were making a function, right? But then you jumped up vertically and continued it right here. So this type of discontinuity in the graph is called a jump. Jumps are always vertical. Jumps are always vertical, okay? All right, so there's your second type of discontinuity. No one ever forgets that name because it's exactly what it looks like. And then last but not least, we have this one, which I technically already drew, right? We know that that is a hole in the graph, okay? So this is called a hole in the graph. You know that from Algebra 2 with trig. But it's not called a hole discontinuity. It's called a removable discontinuity. So how are we going to remember that this is called a removable discontinuity? The reason it's called a removable discontinuity is because one point is removed. That means that if there was a 1 point added, it's now continuous. But if you remove that point, it's now not continuous. So it's called a removable discontinuity. Make sure you can tell the difference between a removable discontinuity and a jump discontinuity. If I placed a point right here, this is still not continuous. Therefore, it's not a removable discontinuity. If I place a point here, it's now continuous. That is a removable discontinuity. So we have three types of discontinuities: infinite discontinuities, jump discontinuities, and removable discontinuities. All right, what we're going to do next is we're going to look at a graph, and we are going to say if there's a discontinuity there. If so, what type of discontinuity it is. All right, so it says determine if the function is continuous at each x value. If it's not, state the type. All right, so this first one's at x equals 2. So we're going to look at x equals 2 right here. And we're going to say, is there a discontinuity there? So we're looking for a jump there, a hole there, or an asymptote there. It has none of those. So there is no discontinuity there. So therefore, it's continuous. All right, let's look at x equals 3. So at x equals 3, there is a discontinuity there. So I need to know if it is an infinite, jump, or removable discontinuity. If you look with your eyes, you see a hole in the graph. So there is a removable discontinuity there. All right, the next one at x equals 1. So at x equals 1 right here, right there. There's a discontinuity there. Be careful, it's not a removable discontinuity. If you look, the graph does pick back up right here. Or it actually starts right here and picks back up at this open point right here. And then it keeps going. That is a jump discontinuity. And then last, but certainly not least, we have x equals -4. Right there, you can see that's an asymptote. There's no points at all right there. It breaks up the function into two different pieces. That asymptote goes on forever and ever and ever. I think of the word infinite. So this is an infinite discontinuity. Okay, so we talked about continuity, which is super simple, right? Just remembering those words, jump, not going to forget, removable and infinite, and you should be good. All right, so the last thing we're going to talk about is symmetry of graphs. So when we're looking for symmetry of graphs, we're looking for three types of symmetry. We're looking for symmetry over the x-axis, we're looking for symmetry over the y-axis, or we're looking for 180-degree symmetry about the origin, okay? So we're going to look at this first graph, and we're going to see, does it have symmetry over the x-axis, y-axis, or about the origin? Now, a graph could have symmetry and not have any of these three. We're not looking for that at all. I want to know if it's specifically one of these three things. All right, so let's look to see if there's symmetry over the x-axis. So basically, I'm going to use the x-axis as a knife. Okay, here's a knife. And say if I cut the graph right there, would the top half fall on the bottom half? The answer is no, so that's no. All right, now I'm going to look for symmetry over the y-axis. So if I look at symmetry over the y-axis, I'm going to use that as a knife. And if I folded the left side over the right side, would it fall on itself? Yes. So this is symmetry over the y-axis, B. Okay. The third one is symmetry, 180-degree symmetry about the origin. This is also called 180-degree rotational symmetry. The way I like to think of this is that if you turned your paper, your iPad upside down, would the graph look exactly the same and be in the exact same spot? Okay, because it have to be about the origin. It can't be moved. All right, so let's look at B right here. Is there symmetry over the x-axis? If I use this as a knife, the top half would not fall on the bottom. Okay, symmetry about the y-axis. The left side would not fall on the right side, so no. Symmetry about the origin. So if I turn my iPad upside down, would the graph fall on top of itself? The answer is yes. So if I turned this, and I think, nope, that's an eraser. I can't trace very well. But if I traced this, I tried my best to trace this, and then I took this and I spinned this, if I I can't turn it. But if I turned it 180 degrees, it'd be easier to do it on a smartboard, it would fall right on top of itself. So this is C, 180-degree symmetry about the origin. Last one right here, if you see, if I cut it on the x-axis, it'd fall on itself. So this is symmetry about the x-axis, which is option A. All right, last but not least, we have to talk about whether a function is even, odd, or neither, okay? So, first part here says functions that are symmetric with respect to the y-axis are even. So if we go back to this, we will in a second, we can tell whether these functions are even or odd, okay? If a function is symmetric about the origin, then it's odd. So if y-axis would be even, origin is odd. So if you look back here, this is symmetric over the y-axis, this is even. This is symmetric over about the origin, this is odd. And this is symmetric over the x-axis, which is not the y-axis, not the origin, so this would be neither. See that? All right, so that's how to tell from a graph. The other way is to tell algebraically, which is what we're going to do here. So to tell whether it is even algebraically, well, the process is the same. It's what you get as the output, okay? So it says, I'm just going to say it in my own words instead of reading what you can see on your screen here. So it says, plug in negative x. So I told you in the opener here that where we're going to use this fact. So this is where we're using it. What you're going to do is you're going to plug in negative x for x. If you get the exact same function you started with, okay, if you get the exact same thing you started with, then it's even. If you get the opposite of what you started with, so everything in that function is the opposite of what it originally was, then it's odd. If neither of those things happen, then it's neither. All right, let's see if you understand what I'm saying here. All right, so example 4, it says graph the function on a graphing calculator, which we're not going to do to start, okay? I can show you after we do the problem in my graphing calculator as long as it's loaded on my iPad. But what we're going to do is we're going to actually start by doing it algebraically, okay? So A says analyze the graph by looking at it to tell whether it's even, odd, or neither. If it's even or odd, then describe the symmetry. We're not going to look at the graph first and do it because this part of the test is all no calculator. So what we're going to do is we're going to do it algebraically and we'll confirm it graphically. All right, so to find out algebraically whether the function's even or odd, we are going to find f of negative x. Sorry, I don't like writing in red. I like blue. Okay, so we are going to plug in negative x for all of our x's, so here and here. All right, so we're going to do equals negative x and then square it minus 4 times negative x and then plus 4. All right, so now we have to clean this up. This is why we learned how to do this a couple days ago and have had it in our opener. All right, so I'm going to start with negative x squared. So negative x times negative x is x squared. Now I have negative 4 times negative x, which is positive 4x. And then I have plus 4. So this is f of negative x. All right, so now I'm going to look at this, and I'm going to look at the original equation that was typed on the paper. I'm going to look to see if it looks exactly the same as the way it started. No. Why does it not look exactly the same? Because this is a negative and this is a positive. Everything else is the same, right? Okay, so it's not even because it's not exactly the same. So now I'm going to see if it's the exact opposite. The exact opposite means that the entire function is the opposite. That means that this would be negative, this would be positive, and this would be negative. So if you look at it, it's not the opposite either, is because this is positive still and this is positive still. This is the opposite, but that's it. So since it's not the same and it's not the opposite, it is neither. Okay? So this is not even nor odd. All right, so now I'm going to show you on a graphing calculator, hopefully. I got to find my graphing calculator. Oh, there it is right there. Okay. I will type this equation in the calculator. So y equals x squared. I believe it was minus 4x plus 4. The original. Hit graph. And if you look at it, so I can't draw on this, okay? And it's, in fact, when I touch it, it goes a little loopy. But if you look at the x-axis where it says 0 right there and the y-axis where it says 0, this is not a reflection over the x-axis. Or sorry, that's nothing. It's not a reflection over the y-axis, which would make it even. And it does not have 180-degree rotational symmetry, so it's not odd. So it's neither of those. Okay, let me get back to my notes here. All right. Let's do the same thing for the next one now that we know how to do it very clear, right? So we're going to do it algebraically. So we're going to find f of negative x, okay? All right, we're going to plug in negative x right here for x. So that is negative x squared minus 5. All right, negative x squared, or negative x times negative x, is x squared, and then minus 5. And once again, that's f of negative x. All right, so let's compare it to the original. If you compare it to the original, this is exactly the same as this. Since they're exactly the same, that means it is even. All right, I'm going to type it in the calculator once again. I'll split screen with it really quickly. Put it right here. All right, so if I go to y equals and I change this, I'll clear it out and retype it. X squared. Nope, that's not x squared. X squared minus 5. Hit graph. And if you look, this has symmetry over the y-axis. Right? It's like if I took the y-axis and put a knife right through it, the left side would fall on top of the right side. So it is even. All right, last one. Once again, we're going to do this algebraically. This is h of x, and the second one was g of x, and I called it f, so I'm going to fix that right now. G and g. All right, so h of x. So I'm going to do h of negative x. Plug in negative x. So I have negative x cubed minus 3 times negative x. All right, negative x cubed is negative x. I'm going to not just say it out loud, but write it out loud. Or sorry, I'm going to write it down. Negative x times negative x times negative x. So realize this is -1, -1, -1, right? The coefficient in front. -1 times -1 times -1 is still -1. X times x times x is x cubed. So I have -1 x cubed, or negative x cubed. The next one I have -3 times negative x, which is positive 3x. All right, so there is my function f of negative x, sorry, h of negative x. We are going to compare that to the original. It's definitely not exactly the same, but if you look, it's the opposite. This was positive, this is now negative. This was negative, this is now positive. So since it's the opposite, odd, this is an odd function. All right, ooh, and I just realized they also said describe the symmetry. So I'll go back and do that to all three of them. All right, so let's go and plug this in our calculator so you can see what it looks like. X to the third power, and then minus 3x. If you look at it, it's going to have symmetry about the origin. So if you look at it, it does, right? If I turn my calculator upside down, it would look exactly the same. All right, so I would be done, but I forgot to follow all the directions where it says describe the symmetry. I don't need the pictures. I know if it's odd, it has symmetry about the origin, or 180-degree symmetry about the origin. So symmetry about the origin, or symmetry respect the origin, 180 degrees, anything like that. Origin. All right. Is that how you spell origin? Origin? Yes, I did forget an I. Okay. All right. Number example 5, even. If it's even, it has symmetry over the y-axis. And the other one, the last one that's neither, I'm not going to say no symmetry, okay? If you are saying like, wait, can't you just say no symmetry? No, I definitely cannot say no symmetry. Because if we go back to this, let me clear this out and retype it. I know I'm working backwards here, but it's fine. X squared minus 4x plus 4 graph. This has symmetry. It has symmetry over the line x equals 2, it looks like. There's symmetry there. It's just not symmetry about the origin or over the y-axis. So please don't say no symmetry. It has symmetry, but it's not even or odd because it doesn't have symmetry about the origin or over the y-axis. So does not have symmetry about the origin or over the y-axis. And those are the words I need to say. If I were taking a test or an assessment and I just put no symmetry, I'd get no points because it does have symmetry. All right, that's it for today's notes. You can go ahead and get started.